Hello, and welcome to the first lecture in the AP Physics C Mechanics series. We're going to go over the first part of Chapter 2. We're going to be covering displacement, average velocity, and average speed. So let's go ahead and get started. Okay, so we know that we find objects that move all around us. The study of the motion of these objects is going to be called kinematics. So a good portion of the mechanics textbook is going to be talking about kinematics, or at least the first bit. Here we're going to be studying the motion that takes place in a straight line. So we're going to start simple. So we don't know that forces cause motion, but in later chapters we're going to get into what forces actually do. What we want to focus on right now is just the motion itself. So if an object is speeding up, slowing down, or maintaining the same rate. The moving object here would be considered as a particle. So we're not going to be worrying about an object rotating. We're just going to be assuming that even if it's a stiff extended object, that it's going to be one particle moving as one. So the location of an object is usually given in terms of a standard reference point, and the reference point is generally called the origin on an XY plot, something like this, where you have two directions. The origin is going to be right there in the middle, and generally the coordinates for the origin are 0, 0. So the positive direction is generally taken to be where the coordinates are increasing. Now the standard convention is that anything to the right is going to be positive, anything to the left is going to be negative. Same way with up is generally positive, down is generally negative. But these can change. You can actually set them to however you want. So if you wanted up to be negative, you can set it that way as long as you define it somewhere in the problem or on your graph. So a change in coordinates is the position of the body a change in coordinates is the position of the body describes the displacement of the body. So as the position changes, you're going to have a change in displacement. A change in displacement is generally notated by this delta x. Okay, and to solve for that, all we're going to do is take the position of x2, which is the final position, and subtract it from x1, which is the initial position. Now sometimes this equation is written like this, where you have xf as x final minus xi as x initial, or just to confuse you a little more, xf minus x naught. Now that little zero down there is x naught. Just another way of saying its initial position or wherever it's starting. So displacement's a vector. A vector means that it has a magnitude and a direction. We're going to get into vectors a little bit later on, but just keep in mind that displacement is going to be different from distance. Distance is just a magnitude, it actually has no direction to it, where displacement is a vector and it also has a direction. Okay? So an object's displacement, for instance, is x is equal to -4, which means that the object has moved towards decreasing x-axis by 4 meters. So for instance, we have our little graph over here, and it's moving along the x-axis. We can call this the x-axis, and for kicks we'll just call this the y-axis. It's starting at the origin, which is right here in the middle, and it's going to the left 4 meters. So its location is -4 meters. Again, to show this position, you could say that the position is -4, 0. 0 would be the y coordinate, which is the up and down. But again, we're just talking about one direction, so we're not even going to be worrying about going up or down at this point. Okay. So a common way to describe the motion of an object is to show a graph of its position as a function of time. So even though we're going to use, and let's zoom in on it, and remove my head out of the way, even though we're going to be using a coordinate system that has two directions, this is really only talking about movement in the x direction, but our other coordinate is time. Okay, not to confuse anyone, time is shown, let's see if we can, no, it's not going to let me draw, okay? So let me go back here. Time is going to be on the horizontal axis, and they put x on the vertical axis. And that's okay, we can do that. All right, so again, just zooming back in real quick. So it's pointing out a couple different points. Now, as we move to the right in this graph, so we're moving to the right, time is increasing. So time is progressing. And position is just shown on the vertical axis. So if you notice in the bottom left, it's saying that the position at x is equal to -5 when time is equal to 0. So that data point is plotted there. So this one right here is going to be where the starting position of the particle is at time is equal to 0. Now as time progresses, it's going to slowly go in the positive direction until it gets to 0, which is going to be the origin. So the origin it hits at 3 seconds. And then as we keep going along, we see that 4 seconds we're at a position of x is equal to 2. So if you just kind of follow this across, you can see that at 4 seconds, which is right here, the position is going to be x is equal to 2. Oops, I'm sorry. Let's go back. So the average velocity, or v average, which is denoted by a v with an avg under it, is defined as the displacement over time duration. So we're given our first, let me move my head again, we're given our first equation down here. And what it's saying is the average velocity is going to be the change in x, which is our delta x, over the change in time. If you wanted to write that out, it's just going to be x2 minus x1, or t2 minus t1. Again, you could also write it, oops, not do that, you could also write it as the average is equal to delta x over delta t, which is equal to the final x minus x naught, which is our initial x, over the final time minus our initial time. Okay. So the average velocity has the same sign as the displacement. All right, so let's try to use this equation. All right, so here's the average velocity. We know that to find the average velocity, we can find the slope of the distance first time. Okay, so we know our slope equation is always the change in y over the change in x. In this case, it's going to be the change in x over the change in t, because we have we have the change in x as our vertical axis and delta t as our horizontal axis. So that's why we can use this equation here. So that's going to give us our average velocity. All right. So just looking at what they did here, they pick two random points. They don't have to pick the first and the last. They can just pick any. So what they did is they picked a point down here and a point up here. And they counted across, or they subtracted the points, however you want to do it. And you get this equation, this equation up here. So your average velocity is going to be 6 meters. Okay, so 6 meters, again, we're starting, you want to take your last point and subtract the first point. So if you did it, your change in x coordinate would be equal to, it starts at 2, and you're subtracting, and it goes to -4. So you're subtracting a -4, which is going to get you a positive 6 meters. Again, same for the time. Delta t is going to be, the last point is going to be at 4 seconds. So we're just going to have 4 seconds. And the first point is 1 second. So we end up with 3 seconds. Okay, plugging this into the equation, 6 meters divided by 3 seconds is equal to 2 meters a second. And notice I kept the units. So I kept the meters over seconds because that's what we divided by. So average speed is going to be different than average velocity. Now velocity is a vector. Again, it's going to have a direction, so it's going to have a positive or negative sign. Speed is just a scalar, so you're not ever going to have a positive or a negative sign. So when you calculate the speed for something, or the average speed, you're going to take its total distance. which means the total amount traveled. Now to show you a counterexample for this, let's say that here's our x-axis here. And we had a particle starting here. And then it went this way, and then it went back. So that its final position was also here. Okay? Its delta x, which is its displacement, is actually going to be equal to 0. Because its final position, which is, let's just call this 0, the origin, its final position is 0. And its initial position is also 0. So you just have 0 minus 0. Okay? But for speed, we're talking about the total distance traveled. So if we did the total distance, it's going this way. Let's say this was 4 meters, and it came back 4 meters, so its total distance traveled would be 8 meters. So for example, we're going to use s for speed, or average speed. So let's say it traveled a total of 8 meters, and let's just say it was in 4 seconds. So you can see the average speed was 2 meters a second, which is different than the average velocity again. Okay, so moving on. Here's an example. So you drive a beat-up pickup truck along a straight road for 8.4 kilometers at 70 kilometers an hour, at which point the truck runs out of gas and stops. Okay, so let's write down our givens first. Whoops. Try to stay on the same page here. Alright, so our givens are that we have a distance, we'll just call this x1 is equal to 8.4 kilometers. And its velocity, 1, is equal to 70 kilometers an hour, at which point the truck stops. So for the next 30 minutes, you walk another 2 kilometers. So let's say our x2 is then going to be 2.0 kilometers, and our t2 is going to be 30 minutes. And let's keep everything in hours since we have our speed in hours. So we'll say 30 minutes is 0.5 hours. Okay? All right. So assume for convenience that you move, excuse me, I forgot the question. So what is your overall displacement from the beginning of your drive to the arrival at the station? So we're trying to find its overall displacement. So assume for convenience that you move in the positive direction of the x-axis. Right? So here's our x-axis. Let's say 0, which is our origin, is somewhere over there on the left. Okay. And we first go a total of 8.4 kilometers while we're in the truck. So we have 8.4 kilometers. Okay. And we know then we'd walk an additional 2 kilometers. Okay, so we drew it out. So the second position must be at 8.4 kilometers plus 2 kilometers, which is a total of 10 kilometers. So when we're adding displacements here, all we have to do, if we can say that our total displacement x is equal to 8.4 kilometers plus 2.0 kilometers, which of course is 10.4 kilometers. So that's our change in displacement. Now really, this is our final position. And our initial position, so we can call this our x final, our initial position is 0, right? So if you wanted to follow this equation here, all it's saying is its change in x, or the change in displacement, is x2 minus x1, which is 10.4 kilometers minus 0.